So today we're doing problem 1.3, which says a concrete wall which has a surface area of 20 square meters and is 0.3 meters thick separates conditioned room air from ambient air. The temperature of the inner surface of the wall is maintained at 25 degrees Celsius and the thermal conductivity of the concrete is 1 watt per meter K. Part A asks us to determine the heat loss through the wall for outer surface temperatures ranging from -15 to 38 degrees Celsius for winter and summer extremes, respectively, and then to make a graph about that. And part B asks us to plot the heat loss as a function of the outer surface temperature for different wall materials instead of concrete, one having a thermal conductivity of 0.75 and one having 1.25, which are 0.25 below and above our concrete, respectively. So let's get started with our knowns. And just reading through, the first thing we know is that surface area, I'm just going to call it A since we have no other areas in this problem, is 20 square meters. We have thickness, which I'm going to call L, is 0.3 meters. We have T in, which is the inner surface, maintained at 25 degrees Celsius. And we have, I'm going to call it K1 because I know we're going to have other Ks later. K1 is equal to 1 watt per meter K. And then we will move on to our find. So we are finding heat loss, which is Q sub X, no primes, for, and then we have a range. So from -15 degrees Celsius all the way to 38 degrees Celsius. This just means the set of all those temperatures inclusive, so including -15 and 38. And then we need a graph for that. And let me mark that that is for part A. In part B, we have other graphs for a different K. Okay, let's draw our schematic of the situation. And our schematic is pretty much just going to look like a plane wall. So I'm going to draw a head-on view of our plane wall. And I'll put a little bit back here with these little squigglies to convey that the wall is broken. And we're going to have T in on one side, and then we're going to have our outer temperature, which for now we will just call T out on the outside. We have our thickness L, which is 0.3 meters, which is the thickness of the wall. We know that we have a surface area A of 20 meters. We also have K, which is that concrete. And then because we have nothing fancy going on here, I'm also just going to draw a line from T in to T out. And it doesn't matter if T out is higher, if it doesn't matter if it's, at the top of our range, 38 degrees Celsius, or if it's -15, we know that there's going to be a linear relationship, meaning we're not going to have any graphs that look like that or that, that would be wild. But because, and this is going to make sense once we get to our equation, is a linear relationship. So let's go do our assumptions. And first, like all we've done so far, we're going to have 1D conduction. You can specify the direction if you really like. We're going to have steady state conditions, since there is nothing indicating to us that this would not be steady state. And we're going to have constant properties. So that thickness, the K, none of that is going to be changed by the heat transfer itself. And that's really all we need. So let's jump to the analysis, and we're going to do part of it on paper here, and then I will jump into Python to do the other part. So remember, we are finding heat loss, and heat loss is Q sub X, no primes. And what's our equation for that? Well, hopefully we're familiar at this point. It is minus K A dt dx. I'm just in the habit of writing partial t, partial x, but it is the same as dt dx And then I'm just going to expand this out a little bit to be a little bit more precise. So K, A, and then instead of dt, I'm going to say T in minus T out divided by L, which is our thickness. And a little note here, so this formula has the negative at the beginning, and you might notice that I put T in minus T out. There is an assumption here that T in is greater than T out. Really, what I realistically do in most of these problems is I kind of just ignore the negatives. And I go back and look at my schematic, and if T out is less than T in, then I say, okay, I know the heat is flowing from T out into T out. But if T out were super high, so if T out is greater than T in, then the heat is actually going to flow from hot to cold, right? So whichever side is hotter is going to flow to whatever side is colder. Bit of an oversimplification, but we're in chapter 1, so I think that should be okay. Okay, and let's start by just doing one example. Let's get our ends of our ranges. So we have minus 15 and 38. So we're going to say Q of x equals minus K, which we said was 1 watt per meter squared. A was 20 meters squared. T in minus T out is going to be 25 degrees Celsius minus 15 degrees Celsius, and L is 0.3. And real quick, I'm going to do that math. So we're going to quickly do that math, and we get an answer of 2667 watts for our upper range. And we'll just very quickly do that exact same calculation again, but, excuse me there. Instead, we were going to use 38. You know what, let's not even do that. So at this point, we can go ahead and move on to our Python portion. The last thing I'll say is I'm just going to write this out in formula. So Qx, dependent on, and there's a couple things we're going to change, and that's going to be the K of the material, and then the temperature outside is equal to minus K times A times T in minus T out over L. And the only things that we have changing are K and T out. So I will catch you in Python.
So here we are inside of Google Colab, and we are just going to start by putting down that same formula we wrote when we were inside of the notebook. So that is Q sub x, the heat loss, as a function of K and the outside temperature is equal to minus K times A times the inside temperature minus the outside temperature divided by the thickness L. And so what we're going to do next is just import a couple of necessary libraries. The first one is NumPy, so that we can do some list things. And the second one here is matplotlib.pyplot, so that we can make some very nice charts for our problem. And we'll just run that really quickly, and that's done. So let's start here with our thermal conductivities. We have a first K at 1 watt per meter K, a second K at 0.75 watt per meter Kelvin, I should say, and a third K at 1.25 watts per meter Kelvin. From there, next we are going to want to create a list full of all our temperatures. So we'll create T out, which is going to be a np.linspace. If you never used it, very useful. Creates a list with evenly spaced samples from a start to a stop. So we're going to start at minus 15 degrees Celsius, finish at 38 degrees Celsius, and we're going to put 100 steps in there just to have a pretty fine graph so that it looks good. Then we're going to calculate our heat loss following that formula from above. So we'll have Q sub x is minus K1 times A, and we'll just start with that first K1. Also, noticed here that I forgot to put some of the other quantities, so we'll put in A is 20 and L is 0.3 meters. And then back to our heat loss, it's going to be T in, which is always 25 degrees Celsius, minus our list T out, and then we're going to divide that quantity by the thickness L. And run that, make sure there are no errors, that's great. And next, for this part A, we're going to start plotting. So we'll do plt.plot. We will go ahead and plot on our x-axis the temperature of the outside. And then on our y-axis, we want to go ahead and plot the heat loss Q sub x. And then we'll just put a couple labels here, matching what we just said, the outside temperature in degrees Celsius on the x-axis, heat loss on the y-axis. And then we're just going to put this last plt.show here to make sure we don't get any weird memory things. And plotting this looks a little bit off. We should have probably expected a line facing the other direction, because we should not have a negative heat loss when we have a negative outside temperature. That would mean we actually end up having a heat gain when we have a negative outside temperature, which doesn't make sense, right? It's cold outside, your house is not going to get hotter. So what likely is the problem here, yeah, you can, at this little corner, is this minus in front of the K. And we even said earlier we're going to ignore that. So if we flip it, great. That graph makes a lot more sense. We should have more heat loss when it is colder outside, and we should have a negative heat loss, also called a heat gain, when it is hotter on the outside than it is inside. And that's part A. So we'll go down here to a separate cell and we'll do part B. Just going to copy this code here so that we do not have to rewrite everything. Paste it. And we're just going to copy the same heat loss list, but we're going to have one for each of our thermal conductivities. So we'll have QX2 for K2 and QX3 for K3. And just change that there and there. And next, we're just going to go ahead and plot all three on the exact same plot. In order to do that, and in order to make it more clear, I'm going to give each of these a label. The first one is 1 watt per meter K. I'm going to do the second one and third one, and change the labels to 0.75 and 1.25 like we have above. Like that. And then to be able to better distinguish them, I'm also going to put a legend on this graph so it shows us which color pertains to which thermal conductivity. And this looks very good, right? So we should expect that this top green line, which pertains to the highest thermal conductivity, should have the greatest heat loss. If our walls are letting a lot of heat in or out, we should expect to have a lot of heat loss. And then that orange line, we expect to be at the bottom, right? A lower thermal conductivity means that this wall material is a better insulator and we should have less heat loss. Real quick, just to finish up, we'll go ahead and put a title on here, make it look nice and professional. And that is problem 1.3.